Hello everyone, my name is Gareth Blytho and I'm a sales specialist for LNP solutions at Unchained Labs. Unfortunately, Ben Knappett can't be with us today, so I will be your moderator. Thank you for joining us. We'll have a Q&A session at the end of the presentation. To ask questions, all you have to do is click on Q&A in the Zoom navigation bar at the top or bottom of your screen and type your question. We will get to as many of them as we can in the time that we have, but when submitting a question, please avoid clicking the anonymous button so that we can reach out to you via email afterwards if we aren't able to get to your question. And now I'd like to hand over to Alex Kerr, Senior Application Scientist for LNP Solutions at Unchained Labs. Today, Alex will walk us through how Sunshine can help you with your LNP optimization and scale up. He will show you how easy it is to screen both formulations and conditions whilst keeping costs down and productivity up, and share some fantastic results of Sunshine in action. And now I'll hand it over to Alex. Hello, Alex.
Hello, Gareth. Thank you very much for the kind introduction, and thank you everybody for joining us here today. Really excited to be talking about the Sunshine. So without further ado, let's jump straight into it because we've got a lot to cover. So looking for the right process and formulation for your LNP can feel like you've been left in the dark with all the options to explore and potential dead ends. Well, the sun is rising because Sunshine can rapidly screen your formulations and process conditions in a semi-automated operation, lighting up the landscape and helping you find your top product candidates quickly. It can also be used to run continuously for larger material batches from sunrise to sunset. So your development process typically starts with the formulation. LNPs are typically composed of 4 lipidic components. The principal component is the ionizable lipid, which typically has the highest molar proportion and is the central part of much LNP IP, and it affects everything about the particle. However, the identity and proportion of each of the other constituent lipids can have major impacts on the efficacy of the formulation. The structural lipid, typically DSPC or DOPE, has effects on the efficacy, targeting, and stability, and interesting alternatives and new ways of using them are constantly generated. For example, the 2023 paper by the Cullis group increased the structural lipid molar ratio from the typical 10 up to 40 mol%, and this saw hugely increased circulation times. The PEG lipid, anchor, linker, and chain length can all be varied to affect the circulation time and efficacy of the particle, and various alternatives such as branched PEGs and sarcosine polymers are also coming into play now. And these are really just a small section of what's being investigated throughout the formulation space. And then your lipid components are just one part of the development story. How you make the particles and the best way to transfer them into larger scale, clinically relevant volumes is just as important. The mixing conditions, what flow rates, mixing types, and flow ratios will be best for the selected lipid carriers, and then the processing options on top of that, everything from your concentration of materials through to your storage buffers, all of these things have an impact on the particle properties too. Investigating all these parameters takes time, money, and resources, so being efficient with all of these is really essential. An Unchained Labs solution to optimizing your LNP formulations is Sunshine. Sunshine is the ultimate in rapid, semi-automated screening. Just load your set of reagents into the sample loops, and Sunshine will automate and collect a set of up to 10 experiments, adjusting flow rates, ratios, and dilutions, all within 15 minutes, with automated cleaning cycles between every experiment. Once that's done, you just load the next set of reagents and get going again. Sample sizes range from 1 ml upwards, so you have huge flexibility in the samples that you produce. Like the other development tool in our Sunny Suite range, the sunscreen, Sunshine uses driving fluid, up here, to push sample packets through the system, leading to no dead volume in the flow path. So you load your total sample volume into the sample loops here, which Sunshine can then aliquot out in the necessary amounts. The sample packets meet on the Sunny mixing chip with optional inline dilution and are then pushed to the automated sample collector, which automatically dispenses the series of samples into either 2 ml or 8 ml vials, or even 15 ml Falcon tubes for when you want to produce a little bit more material. Precision manufacture of LNPs needs precision mixing, which is provided by our range of Sunnies, which are our glass microfluidic mixing chips. These come with a host of benefits: ultra-smooth surface, as low as 5 nanometer surface roughness, which when compared to injection molded chips, which typically have a surface roughness of 1 to 3 microns, really helps to prevent material buildup and makes cleaning the chip a breeze. These sunnies are pretty much indefinitely reusable, and because of that automated cleaning between experiments, that can save you thousands of dollars over a development project compared to with single-use or disposable chips. And different sunnies have different mixing types, more on that later, meaning you can choose the right sunny for your application whilst being confident that you're going to get great results. Here we can see a sample of fluorescein being mixed with water on a sunny 490 Trident T under a black light. The fluorescent sample packet is pushed into the sunny by the driving fluid, meets with another unlabeled packet, and is then pushed out of the sunny by that same driving fluid. So that following slug of driving fluid is serving to clean the flow path, and it's easy to see here how even extremely strong fluorophore is rapidly cleared from the system. The precision provided by the sunnies is so important due to the nature of the LNP self-assembly process. As the aqueous phase mixes with the organic lipid phase, the ionizable lipid, which is positively charged due to the use of an acidic buffer such as citrate or acetate, complexes to the negatively charged RNA phosphate backbone. As the lipid's environment becomes more polarized as the ethanol mixes into the water, the lipids self-assemble around the RNA. The rest of the lipids, as that polarity of the solution increases, then self-assemble around these reverse micelles created by the RNA ionizable lipid conjugate, which entraps the RNA inside the LNP, with the PEG lipid and most of the structural lipid located on the outer surface of the particle. The size of the particle is dependent on how long these lipids have to aggregate and grow during the mixing process. So that's related to the speed of mixing. The key consideration here is that the speed of mixing must be uniform throughout the mixing process. If some parts of the sample mix slowly and others fast, the sample will be polydispersed, either with a broad size distribution or multiple size populations. The exact control of flow and mixing channel geometry in our microfluidics means that the samples are combined in an entirely uniform manner, giving low and highly reproducible PDIs. So let's see some examples of sunshine in action, with an eye to keeping costs and experimental time down. In the first case study, we'll be using sunshine to look at the effects of changing the structural lipid on the biophysical characteristics of the resultant particles. So we used a standard LNP formulation molar ratios and a formulation based on Moderna's spike facts. So you've got all your molar ratios here. The lipid concentration was 10 millimolars and the entropy ratio was 6:1. And we decided to check what the effect changing between DSPC and DOPE would have. So whilst very similar, DSPC and DOPE have some notable differences. They both have C18 chains, but DSPC is saturated, whereas DOPE has an unsaturated fatty acid chain. Additionally, it has a small ethanolamine head group. This means that the DOPE molecule is cone-shaped. So P greater than 1. DSPC, with its medium-sized choline head group and well-packed saturated tails, is more of a cylindrical shape in a bilayer. This means that DOPE can generate a negative curvature in a membrane, whereas DSPC leads to a neutral curvature. At low pH, DOPE can even form an inverse hexagonal H phase, and these negatively curved forms may increase destabilization of endosomal membranes, which improves rates of endosomal escape and therefore transfection efficiency of your particle. It's also been noted in literature that changing between DSPC and DOPE can even affect the biodistribution of the particles, with DOPE showing more activity in the spleen than DSPC. A quick note before we jump into the results that we got. We had to analyze these samples too, of course, and so a great unchained synergy is using the Stunner, which is a combination DLS and UV-Vis system to really boost your sample throughput. This uses just 2 microliters of material per well with no need for dilution, Measuring as we did 8 samples in triplicate for this experiment, we used just 6 microliters of each formulation, which just took a few minutes to load, and then let the stunner give us size, PDI, and cargo concentration, all within half an hour with no additional hands-on time. So that's how we're able to generate so much data so easily. So in this experiment, Sunshine was used to run 2 sets of experiments, one for each structural lipid. Each individual sample was 1 ml, and 4 flow rates were tested for each formulation. So a total of 3 ml and 1 ml were loaded into the sample loops for each set of experiments for the aqueous and organic phase, respectively. The Sunshine then automatically aliquoted the material in the sample loops, mixed them at the 4 selected different flow rates with the cleaning cycles in between, and then collected the sample into 2 ml vials. As you can see here, there was really no detectable difference between the 2 formulations and their response to total flow rates. In fact, they're really remarkably similar to the point where they almost look like replicates. With sizes ranging from 100 nanometers at 5 ml per minute down to around 70 nanometers at 12 ml per minute, and PDIs generally below 0.1 in all cases, apart from the lowest flow rate samples. And so what does this look like cost-wise? 2 experiments generating 8 different data points allows us for huge time saving when screening conditions, as samples only need to be loaded once for each screen, which is a massive time saving. When the samples are running, no user input is necessary. And it's the same for cleaning. Whether or not you're running multiple condition screens, the cleaning is automated, so the user doesn't have to spend any time on it. The reusable microfluidics are also a huge saving on disposable mixing chips, with nothing to throw away apart from the syringes used to load the samples. So Sunshine lets you really expand your sample production flexibility whilst cutting down on costs. Another cost-saving hint, this testing was also primarily carried out with poly-A. So if you're not familiar, poly-A is an RNA analog consisting of only the adenosine bases. Whilst it's not a perfect analog to RNA, the size is somewhat heterogeneous and it has different secondary and tertiary structures to standard RNAs. It's far cheaper than RNA and give you a really good idea of what a particle's biophysical properties will be. So in these particle optimization workflows, it can really help cut down on costs in the early stages. You can see in this case, using standard DSPC formulation, the poly-A particles are essentially indistinguishable from the luciferase RNA LNP run at the same conditions. And all of these samples were run at 9 ml per minute. That luciferase mRNA sample with DSPC was then taken on to transfection. So they were used to deliver the luciferase mRNA into cells and express luciferase for a luciferase assay. And they performed really well. These LNPs showed 10 times better luciferase luminescence than the lipofectamine positive control. So solid result there. Now we'll be having a look at the effect of the Sunny. We get asked about our different chips quite a lot, so it's good to be able to dive into some detail about how they are different from each other and the benefits this can bring. We've selected 3 Sunnies here, the Trident 490T, which has a wide 490 micron mixing junction, a long mixing channel and built-in dilution channel. The other 2 are both an X-type Sunny. In these Sunnies, the aqueous flow is split on the Sunny here, and then meets at a compressed mixing junction with the lipid solution. We've selected one with an 190 micron and a 270 micron mixing junction. So this testing was again carried out on an SM102 based formulation. And as you'd expect, at the top end, the particles are larger. At the bottom end, the particles are smaller. The PDIs are also consistently low from about 6 ml per minute. They're all under 0.1, whereas they're just above 0.1, above that flow rate. However, not all of the chips are acting exactly the same across the range of flow rates. So our Sunny geometry is affecting our particle size at various flow rates. And there's 3 key points, I think, to pick out. 1, where they're all roughly the same size at low flow rates. 2, the 190X Sunny. 2, the 190X Sunny, size drops plateaus at 6 ml per minute around 70 nanometers. And 3, the 275X Sunny with the wider junction levels out at 10 ml per minute. The Trident is still producing slightly larger particles at 12 ml per minute than the X-Sunnies and doesn't show clear evidence of a plateau. So what's the story? One part of the story is pretty simple. The narrower the mixing junction, the higher the velocity of the fluids in the channel. There'll be more energy in the mixing, which will happen more rapidly, and therefore produce smaller particles. Simple, right? But that's not the whole story. At 10 ml per minute, the Trident's flow velocity is still less than 1 meter per second, which is less than 190 X-Sunny at 2 ml per minute, but is producing smaller particles, which raises the question, what's going on? So, at low flow rates, the flow is laminar and controlled. Layers of fluid slip over each other, and mixing is primarily driven by diffusion and the surface area of contact of the lipid stream and the aqueous stream. This mixing is slightly slower than other types, but it's really, really finely controlled, gentle, and low pressure. The Trident Sunny appears to remain in this regime for the whole flow rate range tested. This makes sense, as at 12 ml per minute, the Reynolds number is less than 250. And this is reflected in the gradual, controlled drop in size across the entire flow rate range tested. And the X-Sunnies are a little different. At 2 ml per minute, they also seem to be in a very laminar flow regime, hence their particle size matches that of the Trident Sunny. However, as the flow rate increases, something else happens. The channel expansion just after the mixing junction leads to a formation of eddies in the flow, moving out of the laminar or co-flow regime, while still technically in a laminar flow regime with regards to the Reynolds number. The formation of these eddies induces rapid lateral mixing, which produces very small particles even at those relatively low flow rates. The particles produced on the 190X drop in size faster than those on the 275X, where they reach that plateau earlier because of that narrower mixing junction. That's not all though, because there's always more to think about with LNP synthesis. There isn't too much difference between a 190X and a 275X, as shown here in the pressure logs provided by the Sunny Suite software. So it's a max of about 3 bar for the 190X and 2 bar for the 275X. But chips with smaller junctions will have higher back pressures. So some may be perfect for screening, but you might have to think about changing to a larger mixing junction when you're looking at scale up and continuous manufacture. Finally, we'll be taking a look at taking a formulation through a brief process optimization and then scale it up. Really, this part of the process has never been easier. We're working with a DOTAP formulation using the Trident 490T Sunny with a lipid concentration of 10 millimolar, and again using poly-A for the cargo. So first we did a flow rate screen in triplicate to assess the stability of the system and the ideal total flow rate for these LNPs. Unlike the previous formulations, the PDI stayed even across the flow rates tested between about 0.12 and 0.16. The repeatability of the samples was excellent as well, so we know this is a pretty stable formulation. A flow rate of 9 ml per minute was selected for the next step. This provided particles of really acceptable size and quality. Just quickly as well here, we can compare the SM102 formulations from earlier to the DOTAP formulation here. And you can see the steeper slope of the DOTAP formulation, which intersects the SM102 formulation at about 9 ml per minute. So just because a formulation behaves one way at low flow rates, that doesn't mean that that trend will hold the same way at higher flow rates. So it's always worth exploring the wider space. So we've selected our flow rates and we have our selected formulation, and now we want to make more of it. In protocol mode, as we were using the device before, it's a matter of minutes to make a 1 ml sample or make up to 15 ml. But when you want to reach even larger volumes and explore scale-up and continuous manufacture, Sunshine is there for you too. You just replace those driving fluids with your reaction fluids, set the software to bypass the sample loops, and it's done. The reactant fluids pass through the syringe pumps and go directly into the Sunny, and then can be collected by the automated collector or go straight into another vessel for large-scale collection. So using this setup, we ran the DOTAP formulation at the 9 ml per minute flow rate we decided on earlier. And here we used the automated collector to manually fractionate the samples into 1.5 ml aliquots and produce around 50 ml of material. It's easy to see the consistency of the process is excellent across the run, with really stable particle sizes and PDIs from beginning to end. What's more, the translation between protocol mode optimization experiments and the large continuous batch is really minimal. They're both within 5 nanometers of each other. So that process was incredibly easy for this formulation. So we've gone through a number of ways here to help you unlock efficiency and flexibility using Sunshine for LNP optimization. For example, using low-cost benchmarking materials such as poly-A or lower-cost cationic lipids. Reusable glass sunnies help keep costs down, and small samples with big impact results help you use less material. This will really help accelerate your workflows as well. You can automate series of reactions. When it's running, you can just walk away. And whilst it's doing that, you can be getting on with setting up your dialysis procedure or whatever else it is to help you increase your productivity. Finally, Sunshine allows you to adjust all the different types of ways you might want to mix your LNP, including TFR, FRR, dilution, and mixing geometry, and allow moving from optimization to scale up with no change of equipment. And the Sunshine is just one part of the Sunny Suite. The Sunny Suite has been created from concept for mRNA LNP nanomedicines to make it as easy as possible to scientists to move from early scale screening and particle optimization to GMP manufacture as easily as possible. With sample sizes of as low as 200 microliters on sunscreen up to tens of liters continuously on Sunshine and Sunbather. Any continuous process developed on Sunshine can be immediately moved onto Sunbather, which is our GMP production solution. This uses the same sunnies and the same pumping technologies as the other pieces of equipment, so your development process can really be as seamless as possible. And the consistency across the range, that means that whether you're running 800 microliters or 8 million, you can really be confident in the Sunny Suite's ability to reproducibly produce particles that you're after. So enjoy the Sunshine with Unchained Labs and sail all the way from development to production with the Sunny Suite. Thank you very much for your time. And I believe we hopefully have some time for some questions now.
Brilliant. Thank you, Alex, for taking us through how Sunshine can make life so much easier and much more cost effective in the lab for LNP optimization. We have some great questions that have already been submitted, but if you'd still like to ask one, you can do so by entering it in the Q&A section of the Zoom navigation bar. So, Alex, we have some great questions here. We will start at the top. What is the smallest particle that you can make on Sunshine?
Well, of course, that is going to be highly formulation dependent. Things like playing around with the molar ratio of the PEG lipid you're using or the identity of that PEG lipid can have a massive effect. But when we're working with typical LNP formulations, we've seen particles down to about 40 nanometers that have remained stable, and that's with a relatively high concentration of PEG. Typically, we are producing particles anywhere from 60 to 120 nanometers, depending on the formulations and concentrations involved. So generally exactly where you want to be with LNPs.
Oh, perfect. And can you also make liposomes on Sunshine?
Yeah, actually, we have a number of customers already who are using their Sunshine to make liposomes. So I believe we just released a blog post by the University of Columbia who have used the Sunshine to make various liposomal formulations. And there's various other groups around the world, actually, who are working on technologies other than just LNPs with our microfluidic technology. So there's loads of flexibility there.
And another formulation question for you, Alex, I'm afraid. What other LNP formulations beside SM102 have you made on Sunshine?
So SM102 is our benchmarking formulation because it's easy to use. We know exactly how it behaves, but we have used pretty much everything that you can find in literature, plus a bunch more of proprietary lipids, of course, that people have tested on our systems that we can't share the data from. But yeah, we typically also run with MC3 and ALC 0315 type lipids, C12-200 and lipidoids like that, and as well as some more really exotic ones.
Perfect. How many times can you use a Sunny or reuse a Sunny mixing chip?
Pretty much as many times as you want. Because of the glass construction, it's super, super inert to any of the chemicals that you're going to be putting through it. It's very easy to clean, as we say. That's all part of that automated cleaning cycle. So you're never going to have material sitting in there that can create those larger aggregates. We would say that maybe you'd want to swap it out after really extensive use just to be really safe. sort of every 6 months or so if you're using it heavily, but that's going to be down to how often you're using it and whether you're seeing regular sort of precipitation events or anything like that that could cause deposits in the chip. But really, you can keep on using them for as long as you're happy with them.
Perfect. Perfect. What other consumables are there?
So there's nothing else that we'd define as a consumable, as in single or limited use on the Sunshine. There is a tubing kit and the syringes for the syringe pump that we'd recommend swapping out maybe every 6 months if you're using the device pretty heavily, just to make sure that there's no kinks or snags in the tubing and to make sure everything's flowing correctly.
Fantastic. So another question here. What are you using to clean the sunnies? Water, ethanol, anything else?
So typically the driving fluids would be the buffer that we're using for that given formulation, and ethanol. So that will be what's used to clean the sunny. If you want to give it a more thorough clean, you can absolutely run any number of cleaning solvents through there. So we've run bleach, we've run IPA, we've run stronger solvents through the system to make sure it's got a really thorough clean if it's going to be used in a particularly sensitive application or just to be thorough. But a typical wash cycle is washed by the materials that you are using to drive the materials through the system. And generally that works pretty well because whatever the material is dissolved in is going to be good for dissolving it if there is any buildup of material.
And some questions here about continuous mode. What is the maximum flow rate that we can achieve?
The maximum flow rate is 10 mil per minute per channel. So it depends on the sunny you're using and the exact tubing configuration. But if you're using 2 channels and mixing at a 3-to-1 ratio, then you're looking at 13 mil per minute, give or take. If you're using dilution, that'll be maxed out at 10 mil per minute. So if you're, say, mixing at a 1-to-1 dilution to reactants, then you're looking at 20 mil per minute. Yeah, so that's the maximum throughput with the standard tubing configuration.
Okay, and do you ever see a difference in the particles that are made in continuous mode compared to protocol mode?
That's a really interesting thing to talk about. I'm sure there's people out there who have done work in scale up who could talk a lot about what happens when you move to continuous mode. So we've done quite a lot of continuous testing. We've recently released the Sunbather, the GMP solution that we talked about. So we have to be confident that that can be used to produce larger volumes of material. So we've gone up to 2 to 5 liters of LNP suspension during testing that, I believe. And for the formulations we're using there, which were DOTAP formulations, and then also corroborating that with more SM102 formulations, we didn't see any change in particle size. However, it is really going to be formulation dependent. And depending on what sunny you're using and what the formulation is, you can see a drift in particle size over time. But that's what the Sunshine is for. You can get into that fully continuous manufacture without spending millions on a large-scale GMP piece of kit, doing your first run with hundreds of thousands of dollars worth of material, and then find out in continuous mode at that flow rate on that chip, actually you're not getting what you had been in protocol mode. So yeah, we think that our solution for this is really, really slick. So you'll find out before you move to GMP and manufacture whether that's going to be an issue with Sunshine.
Okay. And a question on quantification. Is the quantification of LNPs possible using your stunner system?
So yes, stunner can be used for quantification. I mean, there's a number of ways that can be sort of paraphrased or passed. So I guess I'll go through them all because stunner can do them all. So stunner uses multi-angle DLS. So you actually sort of get a calculated measure of the absorbance at each scattering angle for each size. So that can be translated into a 0 degree, the theoretical 0 degree scattering angle, which means that you can tell proportionally how many LNPs by volume are in each peak. So with intensity measurements, you can kind of end up with 2 peaks, and you have no idea what the actual amount of material is in each of the peaks. With our rotational angle DLS, you can pick out how much is in the peak you want and how much is in an aggregate, say, whether there's 1% aggregate or 10% aggregates. Those are very different situations. The other way we can talk about quantification is the payload. So the stunner will use UV vis and the really clever unmix algorithm to pick out the quantification just of the RNA, and it can ignore the signals from the lipids, or even if you use it in the right mode, even from any proteins or anything else that might be in solution. So you can quantify your payload with stunner really easily. Finally, again, because of that rotational angle DLS, we can get an estimated particle count per mil. So we can quantify the literal number of LNPs in a solution. We get really good reproducibility on that as well. And it's a pretty difficult measurement, as I'm sure a lot of people are aware. It can be a really difficult number to get a hold of, especially with DLS-based techniques. So we're very proud of that one.
Fantastic. Well, Alex, I think we have come to the end of the session. Thank you for answering all these great questions, and thank you for a great presentation. I also want to thank all of you who joined us today live. If you'd like to have a deeper conversation with our team, please do get in touch with us at info@unchainedlabs.com, or learn more at our website, which is www.unchainedlabs.com. We'd love to connect with you. Thank you again for attending our virtual seminar, and I hope you have a great rest of your day.